So the same idea was replicated by flipping the bits. You can see that till ith position, we have the contribution from parent number 1, right? And I plus 1 and onwards, the solution component for the second parents are there. And of course, for the second child or second offspring, it is the other way around. That means the first I components are coming from parent 1, and the last I plus 1 to nth component, they are coming from parent 1, right? So this is precisely mimicking the binary crossover. And then you could see that there are limitations with this. For example, no matter which random position we select here, the total number of solution it can generate, it is limited. And this method have some difficulty with exploring the whole feasible region, because you are just flipping, you're not generating number. At least in the earlier method, it was exploring the values between CI1 and CI2. Similarly, other ideas came into the picture. One of them was arithmetic crossover, where you actually take a linear combination of the offsprings to generate ith component of the solution, where lambda was a constant. And similarly, this blend crossover was also given. Now, this method, actually, you can see that it explores only within the smaller component to the larger component, right? So let's say if CI1 is value 0.5 and CI2 value is, let's say, 1.5. So this method will generate a number between 0.5 to 1.5. It is not going to explore below 0.5 and above 1.5. This method is even more restrictive, where it only looks at the swapping of the component, not even exploring the space in between or the values in between the smaller and larger of a particular position. This method was also doing that, but this was controlled by a parameter lambda. So alpha blend, this alpha crossover was given to give exploration outside, beyond the smaller parent and the larger parent component value. That means it was trying to explore the value slightly below the smaller component and slightly above the larger component. And if you take this alpha equals to 0, so then this method just becomes equal to this method, right? So in a way, this blends alpha crossover was more exploratory in nature, which is a requirement for any algorithm, be it a classical algorithm or be it a heuristic algorithm, to explore the promising region of the feasible domain. Few more ideas came. Then there's linear crossover, which was again restrictive in nature, and then one extended line crossover, which actually gives exploration on both of the end, because alpha value is between minus 0.25 to 1.25, so that better solution could be found out. Now, all these ideas were good, and they helped a lot to the people who were trying to develop different methods for global optimization. So based on the same philosophy, like defining crossover operators for real coded GA, people also tried to have the exploration in the domain of defining new mutation operator. And as we know that the sole purpose of mutation operator is to give a perturbation, to change the existing value. So in case of binary alphabets or binary representation, it was done by, with a low probability, changing one particular bit, right? If it is 0, it was converted to 1 or otherwise. So the similar philosophy was kept for defining the mutation operator for real coded GA also. And some ideas were given. One of the idea was that just randomly flip the values. That means given a particular solution, just define a random value between the lower bound and upper bound. Again, it was a one of the first few ideas, and where CI follows a uniform distribution. That means it is equally probable to find out value in this interval. A very fascinating idea came later on, where the extent of the perturbation was dependent upon the current position of this acceleration. That means, depending upon how many generation have been passed, so the extent of variability or the change or perturbation, would reduce. So that means in the beginning, because more exploration is needed, so the value of the mutation or jump created by the mutation or perturbation created by mutation would be higher. And as we move forward, if everything goes well, that means your selection and crossover operator, both of them combined together, are able to drive the whole solution, population towards promising region. There is no need to have a bigger perturbation. That was the whole philosophy. If you see that the current solution CI, either you basically perturb to the right, that means you increase this value, or slightly decrease this value with certain probability, and how much should be should be the extent, that is defined by this. And you can see that T is the current generation value, whereas Gmax is the total number of generations. So if starting in the beginning, you will see that this formula indicates, and B of course is the parameter of the distribution. It's a tunable parameter or hyperparameter. So depending upon T value, in the beginning T value would be small and this perturbation value would be large. And as we move forward, in the end, T would be equal to Gmax. So this whole term will not contribute and only this value would be there, right? So this was the philosophy by defining adaptive, mutation operator. So this term adaptive, if you see the literature, it is very prominently used, and people try to find out both adaptive crossover and mutation operator for in the literature of real coded generative algorithm and other heuristic algorithms also, that the things which adapt with time, right? And then there are terms like self-adaptive, operators. So all those things you can search if you're more interested in deeper understanding of these concepts. But this was one of the very fascinating idea. Then people tried with crossover, which not only deal with two parents, but more than two parents. So some of them are this UNDX and simplex, SPX and PCX. PCX actually was a very good idea, because if you see the distribution of these offspring, so these three are the parents, right, in all three pictures. And you can see that in PCX, the clustering or the cloud of the solution is formulated near the parents. So this actually originated with a philosophy called parent-centric crossover, which was very popular and found to be given better result than something called mean-centric crossover. If you see UNDX, this is the mean of these three solutions, and all the solutions are concentrated around the mean of the population, mean of the three parents. And in simplex, you can see that it's uniformly distributed in this region formulated by three parents. So these three solutions represent three different philosophies of generating new solutions. And as I said, that because we are dealing with real numbers and real representation, so there are plenty of opportunities for exploration. So people started with the exploration around the mean of the parents. Then they also tried the exploration uniformly around the parents. And then third philosophy was that it's better to explore the solutions near the parents, because the offspring, because it's a GA, which basically mimics the natural phenomena. So the offsprings are most likely to follow the traits of their parents. So different philosophies were applied. and it was found that some of them gave good results. So particularly this parent-centric crossover did well. If you see the literature, I'll be discussing one of them also. So yeah, so one of the most popular algorithm which is there in this re-encoded genetic algorithm literature, that is this simulated binary crossover. So what happened that the whole idea of binary encoding, which was in kind of discrete domain, was upgraded with the approximation of the same in continuous domain by defining this probability distribution. So now you can understand. The moment we start talking about some of these, at least we started with uniform distribution, right? And slowly, things started moving towards making use of different kind of distributions. So the simulated binary crossover was one such approach where a new distribution for modeling the extent of solutions or generating solutions was defined. So this is the probability distribution. That means you can find out all the things related with the probability distribution. That means you can find out the cumulative distribution. You can find out the random number which follow this particular distribution. And you see that this distribution has only one parameter, this eta, and which is tunable. So given this distribution, the random number which follow this particular distribution can be defined like this. And then come the whole idea of producing the offspring. And it was suggested that using this probability distribution, given two parents x1 and x2, one can define the offsprings y1 and y2 using this formula. And if you see this, it is essentially saying that although it looks like that it is suggesting something around the mean of the parent, but if you see the plot of this probability distribution, you'll find that actually it's a parent-centric crossover, right? So it gives higher weightage or higher probability for generating solutions nearby each one of the parent even in bit, and it's kind of symmetric in nature, and lower probability when you move away from the parents. So together with this, in combination of this, there was a mutation operator was also defined, which is called the polynomial mutation operator. And again, it has one parameter, eta m, and this delta is defined like this, which is a random value or perturbation value. And so given a solution x, you can actually perturb it by adding something to it, and that something is given by this delta multiplied by delta max. So these are kind of delta max is a parameter. So this value would be either positive or negative. That means it could be x plus some value or x minus some value. And the idea again is that you allow smaller perturbation with higher probability. That means, and larger deviation from the solution with very low probability. That means when I mutate a solution, it is highly probable that I'll be getting something in the vicinity, something in the neighborhood of this solution, and very unlikely or with a very low probability we'll be getting something far away from this solution. So this philosophy of mutation was very well captured using this polynomial mutation, and also generating solutions nearby the parents was also captured by simulated binary crossover. So there is a good proof for this also available if you see the research papers. But this method by far is one of the most popular method, and which was further extended to actually deal with problem related to constraint optimization and then multi-objective optimization, and then also many objective optimization problems. So based on that, another exploration was done where a simpler distribution, a standard distribution was used, which is called the Laplace distribution. And if you see this formula, so again, there are two parameters, A and B, and A is called the location parameter, and B is called the scale parameter. So idea was that around the location, or you can say it's the mean value, the office springs or the solution generators, they are exponentially distributed around this location. That means that with a very high probability, if you apply crossover, it's the way it is used to define new solution. It is a parent-centric crossover where the new solution would be produced quite near to the existing solution, and with a very low probability, you can have solutions away from the parents also. So using this probability density function, one can define the cumulative distribution function, and then we can use this CDF to find out random numbers which follow this distribution. So you can see that this is the plot for Laplace distribution, and with different parameter values, you can see that when B is larger, the concentration of the solution is lesser, because the height is less and the spread is more. And when B is smaller, it gives you much more localized search. So now you have, using this tunable parameter B, you can actually fine tune the production or the generation of solutions nearby. If you want more localized search, it's better to give smaller values of B, and if you want more exploratory search, you can give a larger value of B, right? Similarly, in SBX also, this tunable parameter eta C actually does the same job. Now, so how do we define the parents? So suppose we have given two solutions, x1 and x2, right? And using this x1 and x2 and this Laplace distribution, we can define generation of parents, which is called Laplace crossover, and which says that you just take the first parent and a number beta, which follows the exponential Laplace crossover, Laplace distribution, and then just multiply this with the extent by which these two solutions are far away for each component. So for ith component, you just add to the ith first component, first parent's ith component plus beta times its distance among the two parents. Similarly, the second parent plus beta times the distance between the two parents. So this formula, now you can see that naturally it looks like we are exploring around the parents, right? We are adding something into the parent, and this beta values basically are given here, right? How the betas are generated. So these betas are nothing but a number which follow the exponential or Laplace distribution, and A is taken to be 0, right? The location parameter is taken to be 0. So essentially this whole thing depends upon B, right? And as I told that, depending upon value of B, you can do a localized search around the parent or a much more exploratory search around the parents. So that's a parent-centric crossover. And if you see the properties, I've already discussed these things. Similarly, okay, yeah. One more thing I wanted to discuss is that, as I said, that small value of B offsprings are likely to produce near the parents, and for large value of B, offsprings are expected to produce far from the parents. The second thing is that when you fix A and B, if your A and B are fixed, then the offsprings are proportional to the spread of the parents. That means if I just fix B here, the only change would be based on the distance between x1 and x2, right? That is the thing which is governing the production of the new offspring. So let's take this thing. So if the spread of offspring is far away, then this distribution also would be far. It would be well spread. And if the offsprings are parents are very close, then of course the offspring would also be very close. So these are the two properties which are very much available with this this particular crossover. And so this was all about finding the new solutions, right? Crossover operator. Now there was also a requirement for finding mutation, and for mutation, okay, I'll come to that later. So the other one, heuristic crossover, probably I have discussed earlier. If you see the formula for simulated binary crossover, you see that two parents x1 and x2, they basically produce two offspring y1 and y2. Okay, right? Similarly, if you see the Laplace crossover, two parents x1, x2, they actually produce two parents y1 and y2, right? Now in heuristic crossover, what happens that we have two parents x1 and x2, but they produce only one offspring, and the rule which is followed is that you take the difference between x1 and x2 and take a uniform random number between 0 and 1, and then add this value to x1, right? Now, how this x1 and x2 are chosen is that you have taken x2, the parent which has fitness value not worse than parent 1. That means when you select two parents, for the sake of nomenclature, x2, the second parent, is the one which has either equal or better fitness, right? So basically you are subtracting from the better solution, better parents in terms of fitness, and then you are adding to that, right? So basically this is kind of, in a way, you can see that we are again adding something in the vicinity of x1, but now instead of using some other distribution, we are actually using the uniform distribution. Again, it was a very popular choice and it gives good result also. There is no tunable parameter. For example, in this, even if we take a is equal to 0, b is a tunable parameter, right? You have to fix value of b based on your experiments, or you have to do some computational experiment for that. Similarly, here it has a tunable parameter eta c. Whereas in heuristic crossover, although two parents are producing one offspring, but there is no tunable parameter. So that makes it good choice if you are not interested in doing a lot of number crunching. But side by side, there could be a drawback in terms of exploration, because the exploration which is done using uniform distribution is completely different from the one it is done by some other parent-centric distribution, right? So the important thing, there is only one offspring which is produced, right? The second thing here is that if you see, if you use this formula, because we are adding a vector, if we talk about all the components, it may happen that after producing yi, this yi may go beyond your limit ai bi, right? It may be more than bi or it could be less than ai, right? And if that happens, so the way this heuristic crossover work is that you basically count such failures. So for example, you pick up x1 and x2 and you apply this crossover. That means you find out a random value ui. Now applying this formula, if somehow yi comes out to be either more than bi or less than ai, that means you are violating the bounds, then you basically start counting that how many times it is. So this violation of bound is counted as a failure, and you count for a fixed pair of parents how many times you failed, and then you basically keep a upper bound on that. Let's say k is the upper bound. I will try k times producing new offsprings using the same set of parents, and if all the time I failed, nothing will be produced. That means I have to drop this idea, right? So that is why it is written that heuristic crossover produces at most one office spring, right? Because there may be failure also, because it may violate the bounds also. And in the previous cases, if you see, nowhere here I have talked about that x1 and x2. What is the quality of x1 and x2, right? We have not used the fitness value of parent 1 and parent 2 to produce the office spring, right? So when selection was applied, after that, for applying crossover, the fitness value was not seen, right? So it is perfectly random. That means x1 and x2, they are picked up randomly, right? And because both the formulas are symmetric, so there is no preference or no use of fitness values afterwards. Similarly, in Laplace crossover also, you can see that the parents x1 and x2, they are basically picked up randomly. And once you are picked up, for producing the office spring, we are not using any idea or any information about the fitness value. That means how good these two solutions are, right? But in heuristic crossover, the very formula of crossover actually depends upon the fitness value, because this x2 is the parent which has better fitness. So that is also which makes heuristic crossover quite a different from the other two, right? Now, coming to the real coded mutations, which were kind of very, which gained popularity, there are many other options. I'm discussing only a couple of them, right? So one of the idea was this mutation operator, which again actually gives you a linear combination of the values between the lower bound and upper bound of this solution. That means xil is the lower bound. Essentially, in the last slide or last slide, it was AI, and xiu basically is the upper bound, that is bi. And what we are doing, we are basically trying to produce a number between xi lower and xi upper using this formula. But now TIs are nowhere uniformly distributed, right? They actually follow this particular formula. And if you see that, it says that if you basically generate a number Ri and then try to see whether Ri is less than equal to Ti or not, right? Ri is a number between 0 and 1. And Ti again also is a number between 0 and 1. And you apply this towards the left side or towards the right side, or you do not do anything. It is just equal to Ti, depending upon what you are getting. And again, it has another tunable parameter b, right? So it actually gives you some probability for perturbing towards the right side and some probability for perturbation towards the left side, depending upon where you are located in this interval xi lower to xi upper. If you are close to the upper bound, then the probability of this basically is lesser compared to the more on to produce on the left side. So it basically tries to make a balance. If you are more towards left, it will give you more priority towards to go towards the right hand side, and so on. So what this is the TI value, right? TI is the relative position of current solution X in this range xi upper to xi lower, right? So it would be perfect if you are at the middle point, right? Otherwise, TI value will change. So if you are more towards, let's say, your lower bound is, let's say, 0, upper bound is 1, and you are at point xi is 0.75, so you are more towards the upper bound, right? And then depending upon where you are, you'll be using one of these values. Okay. Now, so how this is different from non-uniform mutation operator? Unlike non-uniform mutation operator, the strength of this does not decrease as the generation increases. You see that nowhere here any information about the generation number is used. It is independent of how many generations the code is running for, or which particular part of this evolution process you are in, right? In non-uniform mutation, if you see, it was actually, the perturbation was actually function of the current generation, right? That means it was variable. The extent was variable and it was diminishing as we move forward. Whereas in this particular mutation operator, this was not the case. Okay. So that makes it different from non-uniform mutation. And yeah, so this again, same non-uniform mutation formula is here. Now, so there was another idea which was floated along with the Laplace crossover, because I defined Laplace crossover. I did not define any combination of mutation. So a simple idea was floated where perturbation actually was given using the power distribution. This power distribution is, or power law is, one of the popular distribution if you see the literature in statistics. And so using this power distribution, the mutation was defined. So this is the CDF for the power distribution. And using this, one can find out a random number which follows power distribution. So this has only one tunable parameter P, right? So how it is defining this? So given current solution X bar, we try to find out a number S which follows the power distribution. And then depending upon whether you are on the right hand side or uh, depending upon this value T, again T is similar to the previous formula, right? Like this, we try to perturbate the solution. Again, if you are more towards right, the probability of perturbing towards left would be more, right? So that you float in the range with good probability. So S is a number, random number which follows power distribution, and xi minus x bar minus xl is the extent by which you're floating. And you see that x bar minus xl would be a positive value because x bar lies between xl and xu, and here also this is a positive value. So essentially this whole formula is trying to subtract something from x bar, and here we are trying to add something to the x bar. Yes, please come again. So in totality, we are trying to give perturbation either towards the right side or to the left side, and the probability of that perturbation actually depends upon the relative position of the current solution, right? It is not dependent upon the current generation number. That means, again, this is not taking into account at what extent of the exploration process you are in, but it is using a simple principle, the standard power distribution, to give perturbation to the solutions. So the strength of mutation is governed by the index mutation, right? If P is less, small value of P give you less perturbation, and larger value of P are going to give you more diversity or more perturbation, so that you can explore the region more efficiently. Also, the probability of producing a mutated solution on the left side is proportional to the distance of x bar to xl, and of course on the left hand side also, depending upon the other thing. And the mutated solution is always feasible. That means when you apply this formula, you are actually subtracting something. It must not pull this solution below xl, or in this case it should not push the solution above xu. So the way this is designed, it is not going to do that. Similarly, the previous result also, it's not going to kind of make solution jump out of the feasible bounds. So that is how it is defined. Yeah, of course, the problem which we faced in heuristic crossover, that may come here in either in Laplace crossover or in simulated binary crossover, because they are not giving you a solution which are bounded in the given range. So some heuristic procedure has to be applied. So one of the processes that we again find out a new solution, that means find out a new beta, so that this thing remains in the bounds. Or in some cases, you can apply heuristic rules that if something is going beyond the bounds, so you give the value equal to the bounds. For example, if the value yi is more than the upper bound, so you assign this yi equals to upper bound, right? So different ways are there to tackle with this, and later on people try to find out the modification in this so that actually the solution do not violate the bounds. So those kind of methods are also there. Now with all this, so we have seen that we defined different kind of real coded the representation is same, it is only real encoding, but the crossover, there are many options. Similarly, for mutation, there are many options. Some of them follow one particular philosophy and other follow the other. But now there is, a big, opportunity to kind of find out the combination also. Right? For example, simulated binary crossover was actually given along with this polynomial mutation, right? This was the combination. And this Laplace crossover was given along with the power mutation. Crossover was given along with some other non-uniform mutation, right? So different combinations were given, but later on people tried to have kind of different combinations also were tried. So for example, people tried applying heuristic crossover with some other mutation and try to see that which one is a better match, right? So all those things, if you look around the books and literature, these things have been tried, and some of them are having much more successful result in some class of problems than others. Now, having said all these things, we have still not discussed. These all are trying to, sort out the issue of, finding solutions for unconstrained problem. Unconstrained problem, when I say, that means there are only bounds on the decision variables, xi lower and xi upper, or ai and bi. But apart from that, there is no other bound. So these are also called box constraint if you see the numerical optimization literature. But then there are many more opportunities to actually look at solutions to the problem which are having much more restrictive environment, and that actually gives to rise to the problem where we have to be very careful in exploration, because you see that the left side picture represent a region which is now no more a rectangular region for exploration, right? It is not a region which is defined by, let's say, for a two variable problem where x1 lies between a1 and b1 and x2 lies between a2 and b2, because it's not a regular region, it is a irregular boundary, right? The problem becomes even more difficult when actually you have this region and there are it's not connected. That means there are holes in this region, right? So the very idea of applying heuristic methods, which do not have good mathematical properties, to the problem which do not have good mathematical properties, because these problems cannot be tackled using hello. Yeah, so we're talking about the problems where actually there is a disconnectedness in the physical region, right? And that's a altogether a big area of research, and lot many techniques have been applied to, along with finding good exploratory search techniques, finding good selection mechanism, finding better representation scheme, finding better crossover mutation operators, finding and applying some local search techniques also, right? There are hybrid methods. But then many of them actually tries to reach here, where constraints are also available. So this is altogether different areas. So I'll stop here. Maybe we can have some questions if you have anything related with this. Any questions?
Participants, if you have any question, you can write in chat window. So, yeah, Dr. Manoj, it seems there is no question. Participants are writing no, sir, in the chat window.
Okay, thank you, Professor Rahul. Thank you very much.
Yeah, so, wait a moment, Professor Manoj. So, participants, if still you have any question or any doubt, you can always write to Professor Manoj on his email also. And Professor Manoj, on the behalf of the organizing committee and on my personal behalf, I'm very much thankful to Professor Manoj for delivering this lecture at our FDP. And Professor Manoj, whenever you get time, please send the PDF file of your lectures so that we can upload it on the Canvas platform.
Okay, thank you, Professor Rahul.
Yeah. Thank you, sir, for a very wonderful lecture. Thank you. Now it's the time for another lecture, and Professor Shiv Kumar Gupta has already joined us. Professor Gupta, can you hear me?
Yes, Rahul ji.
Okay.
Yeah.
So I welcome you, Professor Gupta, here in this our online FDP on numerical methods, computation and optimizations using C and MATLAB programming language.